To consider the possibilities and problems of different sources of energy, it is first necessary to understand what is power and what is energy. We'll concentrate in the basic concepts, using simple expressions, for those who have not studied physics or have forgotten it. To do that, we'll call things by the names used in everyday language. Metric units are used in this document, because comparisons are easier with them. Concerning weights, we'll talk for instance of a kilogram. For that, we'll refer to the weight of a liter of water on our planet, of course. Or the force needed to hold a bag of 1 kilogram of apples, about 2.2 pounds. In technically correct terms, rather than simply saying kilogram, we should have talked of a kilogram force. Or better, of a certain amount of newtons, in honor of the physicist who described the essential laws of forces, their effects, and their relationships. But, as it seems easier to handle familiar words, we'll talk of kilograms or pounds, and let Newton watch his apples. The first drawing shows one of the many forms that a force can be manifested. When we hold an object of some kilograms, we are actually supporting a vertical force of that value. If that object hangs from a spring, it will stretch it. If we want to raise the weight to a certain height, we must spend energy, be it with an electric motor, or just with our muscles, or using a roller. Any object that has been raised acquires a potential energy, and if it is left down to where it was, it will return the energy that had received. If we let it to freely drop, when the object comes down, it suddenly releases that energy, which will be spent on breaking itself or perhaps breaking the floor or our head if it falls directly on it. But, if that weight had been raised only a small amount, say 1 centimeter, the potential energy it had acquired, and then transferred to our head, would have been much smaller. It could imply a nuisance but nothing more. Suppose that we have a tank with 100 liters, about 22 or 26 gallons, depending on which gallons we talk, of water at ground level, and we want to give the water more potential energy, to allow it to come out from the taps with good flow. To elevate the water to another tank, located for instance at a height of 10 meters, over ground level, we'll have to do a work. Naturally, this work depends on the weight of what has been raised, and the height to which it was taken. The necessary work, to raise 1 meter, a weight of 1 kilogram, is considered a kilogram meter, which is the product of 1 kilogram, weight, or force, by 1 meter, the path we went over, against the force. Let's work a few figures with one real example. In the case of the tank, to raise 100 liters of water, weighing 100 kilograms, or kilograms force at a level 10 meter higher, the work required is the product of the weight of the 100 kilograms by the 10 meters of the increased height. The result of this multiplication is 1,000 kilogram meters, which expressed as energy consumption represent, neglecting all losses, 0.0027 kilowatt-hours. Actually, the losses are never negligible, but it would unnecessarily distract us to take them into account. What is important is the reasoning process that follows. Those 1,000 kilogram meters, or 0.0027 kilowatt-hour, can be supplied with a small pump, for example of 0.0027 kilowatt, or else with a bigger pump, for example of 1 kilowatt. The small pump, which operates a power of 0.0027 kilowatt, has to work for an hour, to give enough energy to the total water to be elevated. The large pump requires a power of 1 kilowatt, but would only have to work 0.0027 hours, what is 9.7 seconds, to supply the necessary energy. In short, the same energy can be achieved, little by little if the available power is small, but faster if the available power is great. It is clear that energy is what we had to spend to do the work, and power is what allows us to do the job more or less rapidly. Power is measured in watts, and energy in watt-hours, or the respective multiples, either kilo or megawatt, or kilo or megawatt hour. Not always you can wait long to achieve a certain result. Sometimes it is essential to have a great power, like to rapidly accelerate a car from 0 to 90 km by hour. Other example, for heating one fixed amount of water, a 2 kilowatts water heater will take half the time than another of 1 kilowatt. The power rating of an electric generator connected to the net indicates its potential to rapidly deliver energy to consumers. Usually it is measured in million watts, megawatts. Wind generators currently manufactured can provide the power of 1 megawatt, although there are available others much more powerful. So long as there is enough wind, that power will be enough to feed a group of 300 houses whose agreed limit of power availability is of 3.3 kilowatts. Or probably to 1,000 or more houses, because the houses never require all the time the maximum contracted power. The thermal power plants can be of different capacities, as well as the hydraulic, which can function in quite extended ranges, especially since each plant can have several independent turbines. Each type of plant has its special characteristics. The applicability for a specific country has been, at least partially, covered in other sections of this series. That depends on the geographical or functional concentration, its availability in normal operation or facing any abnormalities, their ability to complement with other systems, and the flexibility to adapt themselves to different loads when power requirements change over time, which is directly related to complementation. Currently there are not medium or small approved nuclear power plants available. They are of 600 megawatts or more. Nuclear plants are also not flexible. Usually they only work between 80 and 100% capacity. Going back to the basics, power is measured in kilowatts, representing the ability to supply or use energy. The energy is measured in kilowatt hours, and indicates how much was really supplied or used in the form of mechanical work, heat or whatever. To interpret an electricity bill, sometimes we find that there are two types of charges. One is a fixed tariff for the contracted power, that is the maximum that the company would be committed to supply. This amount is related to the investment they had to do to deliver the power when the subscriber needs it. A second charge is for the amount of kilowatt hours actually consumed, that is the energy actually used. Normally this amount is the biggest in the bill, or eventually the only one, depending on the companies. In the example of the elevation of water, we didn't want to consider the losses, to focus our attention on the essential concepts only. But in any energy processing, or transmission, there are losses which can represent significant percentages. Just to circulate over the lines, a small part of the transmitted energy is lost as heat in the cables, because they always present some small resistance to the current. Any increment of energy flow requires thicker, more expensive lines. So when you need more power available, the necessary investment in generating equipment will be bigger, and so will be the distribution lines and equipment. All those costs would have impacts in the fee. By reducing these losses, generation facilities that are close to the points of use are more efficient. Distributed net systems can help in that sense.